We
are Team B.A.M.
My name is Brian Gann, and I'm in the 10th grade. I like to work with computers, and I like to play ice hockey.
My name is Aditya Dutt, and I'm in 9th grade. I like to play the violin, and I also like acting on stage.
Hi, my name is Mannan Bhardwaj, and I'm in 6th grade. I like to code and play tennis.
We are competitors in Robocup Junior Rescue Line League. The purpose of the challenge is to design a robot that can trace a line, overcome obstacles, and maneuver around colored turn signals. Then, we enter into a room where plastic balls represent human victims that our robot has to find and drop off at an evacuation zone. We met weekly to work together, and since isolation, have relied on online communication tools to keep in touch and collaborate on our work. We have multiple sensors and motors on our custom robot. We 3D printed the chassis, which supports the rest of the robot. A robot has 2 wheels, each powered by motors coupled with Hall effect sensors acting as encoders to accurately measure our wheel's movement. We have a caster wheel on the back for balance. On the underside of the robot, the camera can be seen. We use the camera, along with the Raspberry Pi, to analyze a video feed and detect the green-colored turn signals. We also have an infrared light array mounted on the bottom of the robot. This measures the reflectance of a surface, and we use it to get an accurate position on the line. On the front, an ultrasonic sensor can be seen, which we use for detecting obstacles and for distance measurement in the evacuation room. We have a servo on the front with which the camera is turned. We have our camera in the down position for the main room to detect the green turn signals, and we use the servo to turn it up to face forward for detecting the victims in the evacuation room. We would also have a servo mounted in the back of the robot to control our mechanism to pick up the victims. For processing, we have an Arduino Uno. The Arduino controls the motors, servos, and sensors. The Raspberry Pi has a serial connection with the Arduino, and when it detects the green signals, it sends a command to the Arduino to execute a turn.
So here's how the claw would work. So right now, a servo would be attached to this right here, and this would be attached to the robot. So this would rotate, open up like this, and then it would close around the ball, and then the robot will move to the triangle while this stays closed, and then once it gets to the triangle, it opens back up again and leaves the ball there.
When we did line tracing, we first needed to find the line. To do that, we used a light array with 8 light sensors on it. The algorithm we used to line trace was the PID algorithm. Basically, this algorithm uses 3 mathematical functions to change how the robot responds to the line. It uses a linear aspect, a derivative, and an integral to impact the motor speeds of each wheel. For example, when the light array sees the line too much to the right, it will do a sharp turn left to get back on track. For the 90 degrees turns, the robot will go off the line, but then it'll detect which direction it left the line off in by looking at the last time it was on the line. It then turns 90 degrees in that direction.
One problem we faced was when the robot encountered a few sharp turns one after another. The robot would think that it was a turn in the opposite direction. Then, it saw that there wasn't a line there. Because of this, it would think that it was a gap and turn back around trying to catch the line. This was fixed by improving our algorithm for the gaps. In the new algorithm, it would turn in the direction it thought the line went. Then, it would check if there was a line there. If there wasn't a line, it would turn more than 180 degrees in the other direction. This would check for a sharp turn going the other way. If there still wasn't a line, then the robot knew that it was a gap. It would face forward and move until it saw the line again. Our Raspberry Pi is connected to the camera, which returns a video feed to the main Python script. For each frame the script receives, it does these following image manipulations. We first convert the image, which is in BGR format, to HSV. We then create a mask of the frame that only includes pixels that have a certain HSV value, which we have set to a range that corresponds to green. Then, we detect contours, or large groups of pixels with the same value, on that mask. This returns any green squares if there were any in that frame. If not, then we take a new frame. If there were any green shapes, then we move on. We remove all the contours that are below a certain size threshold. Then, for each contour, which we can now safely consider a green square, we look at the regions directly above, to the right of, below, and to the left of it. We see if there's a black line in that region. This will tell us where the green square is with respect to the black intersection lines. Then, we just count the number of green squares, and depending on their positions, we can tell which direction the robot has to turn, and we send the corresponding command to the Arduino.
It first checks if the left is a clear path to go. If not, the robot goes right. The algorithm maneuvers the robot around the obstacle until it finds a line. Once this line is found, the robot stops, turns, and resumes the line tracing program.
The algorithm for detecting the silver tape at the end of the line is very similar to that of detecting the green squares. The image is put through an HSV filter. This filter removes anything that has color to it, and this is done by keeping a low, tight range of the hue in HSV. Then, since silver appears gray on camera, the bright whites and the dark black is removed. This gives a mask of anything that is silver. Then, contours are found on the mask, and if a contour is bigger than a given size, which indicates that it isn't just noise, the command to stop is sent to the Arduino.
Black balls are very simple to detect. In our program, we used a binary threshold and checked that the shape resembled a circle. Silver balls are a lot more difficult to detect though. First, the image is converted to grayscale. An adaptive threshold is then applied. Since the silver ball reflects light, the adaptive threshold ends up creating a lot of mini spots on the image where the ball is. This is a problem because this would just result in a bunch of very small contours which would all be discarded because they are too small. Dilation is used to fix this problem. When the image is dilated, all of the small spots combine to form a big spot which creates a circle resembling the ball. A contour is then created out of this dilated image. Finally, the program then checks that the contour is big enough and checks that it's a circular shape.
In the evacuation room, to first find the ball, our robot will keep on turning a couple degrees until the camera sees the ball. Since our robot is circular, it will not collide with anything. Once it sees the ball and points directly at it, it will approach the ball until it's close enough to be grabbed. After it's grabbed, it will start to look for the triangle. Again, it will keep on turning until it sees it. It also makes sure it isn't circular, because that means it is a black ball, not black triangle. When it detects a triangle, it will go towards it and drop off the ball. The robot will keep on repeating this until all three of the balls are in the triangle.
We thought about some areas that we could improve in. Something we could improve upon is the speed of the detection of the green squares. We could do this by making the image processing more efficient, by making the image smaller, and by trying to do fewer manipulations of each frame.
Next year, I'd like to improve on trying to detect the silver tape. Instead of using a camera, I would like to use a light sensor to detect the reflectivity.
Another thing we could improve on is the ballroom navigation. We could do this by implementing multiple cameras which would allow for easier navigation.
Thank you.